Thank you. So, IFA is the International Federation of Airworthiness. We have had our 50th birthday. So it started in the 1970s, mainly actually interestingly focused on licensed engineers and the maintenance environment. So over the years, IFA has embraced both continuing airworthiness and initial airworthiness. So many topics. It is an organization dedicated to covering the whole subject of airworthiness and aircraft safety. Airworthiness being a foundation stone, I think, to aviation safety, because if the aircraft are not fit to fly, then you're not going to be able to achieve your safety objectives at all. So it's an absolute fundamental, really, in the aviation safety equation. But we work closely with our other colleagues in ATM and Ops to ensure that there's good consistency and interaction between the different disciplines, but we are predominantly an engineering organization. We're also a UK charity and a non-governmental organization, so membership driven. We thus depend for our income on our members and any donations that good people may be inclined to give us. We have a trust fund as well, but as I say, I will emphasize the fact that we do need to be resources to be able to continue these types of activities, whether they are webinars like this, technical communication, or whether attending meetings, participating in aviation safety events. As I say, we do need to encourage you to come on board and join the IFA family. And there are quite a few benefits of membership. We publish a newsletter on a regular basis to keep people informed. We run free seminars like this. And so we try and give our members some value for money in terms of their membership. Thank you very much for coming on board today. As I say, it's a great opportunity, I think, to visit the subject of aviation aircraft maintenance. And we have a speaker here today who's studied the subject in depth. So Rajdi is volunteered to step forward and tell us of his findings and experience in terms of looking at aviation safety data and seeing what he's distilled from the messages that are out there. The flow of information, the flow of data, and the proper analysis of that data, I think, are absolute fundamentals both to airworthiness and to aviation safety. And so what we can learn from that process, I think, helps us all in the future challenges that we have. So we're now about 7 minutes past. I think we've got only about 8 people on board. Hopefully a few more people will come on board as we progress. So I think I might hand over now to Raj, if you're ready.
Sure. Sure.
Introduce yourself and let us know a little bit about you and how you came to be in this particular role, and then the floor is entirely yours. Thank you.
Thank you very much, John, and good afternoon, everyone. Thank you for your time today, and thanks to Cengiz and the IFA team, John and Michaela, for inviting me to share my presentation. My name, as hopefully you can see my screen, my name is Raj Day, and I currently serve as a Group Head of Aviation Engineering Standards at Babcock International. My role involves setting engineering standards across a broad and complex operational environment, where, of course, safety, compliance, and operational performance must all be balanced on a daily basis. Having worked both on as an engineer and later in senior leadership roles, I've had the opportunity to see maintenance from both the perspectives, how tasks are actually carried out in practice, and how they are designed and assured at an organizational level. Just before I start introducing onto my thesis or presentation related to my thesis, may I request that all the questions be saved to the end of the presentation, where we can ask questions through either chat and or the voice method. So the work I'm presenting today forms part of my MSc research at Cranfield University, supported by easyJet, that was my previous organization, and has also been published this year in the Spring of Publications. I will share the link to my paper at the end of the presentation. The motivation for this research came not from theory, but from real operational challenges, especially repeated maintenance events where controls were in place, the risk controls were in place, yet errors still occurred. I believe this is something many of us in this virtual room will recognize. We invest heavily in procedures, training, and compliance frameworks, and yet from time to time we see events that are difficult to fully explain and even harder to consistently prevent. That observation led me to explore a fundamental question. How do we know that a maintenance task has truly been completed as intended? Because in most cases, what we rely on is certification. And certification tells us that a task has been signed off, but not necessarily how well it was performed or whether it fully achieved its intent. So the focus of today's presentation is how we can enhance the feedback loop, especially around the critical aircraft maintenance tasks. When we think about maintenance safety, we often focus on procedures, we focus on compliance and certification. But what I wanted to explore is what happens between the task being completed and the organization actually knowing with confidence that it was done correctly. Because it is in that gap, that uncertainty, where risk exists. And to explain why this matters, let me take you through a real world example. Now this example, for some of my previous colleagues who may have joined from easyJet may know about this event. But before I introduce you to the subject of my thesis, I thought I would take you through, along with me, through the journey of why I think this subject is really important. So this is based upon a true story. This was a normal weather day in the UK. I'm not sure what's the weather like outside for you today, but a normal weather day in the UK with lots of rain and wet weather conditions. An aircraft, I've changed the name to protect identity. Let's say it was Golf Alpha Alpha. This was released from maintenance from one of our contracted bases in the UK and was ready in the morning for a flight to Alicante. There was nothing unusual reported. Alicante, on the other hand, was predicting a sunny and bright weather with temperatures of around 27 degrees. Our flight was full with excited passengers wishing to go on an excellent vacation. The flight departed on time and was cruising well into its journey to Alicante. It is around at this time, around mid-flight, that our power plant engineers at our office in London received an engine alert for engine number 1 on Golf Alpha Alpha. This is, as you know, through an ACAS system receiving live data from the aircraft for engine trend monitoring purposes. Now this was an engine cowl temperature shift, meaning there was a step change of the monitored temperature in the engine cowl region, which consequently meant that there was a risk of an engine fire. The message was transmitted from the ground to the crew of Golf Alpha Alpha, and it was decided that the aircraft should fly back to the maintenance base in the UK from where it took off more than an hour ago. During its flight back, the situation escalated further as the crew received a fire warning in the cockpit and they had to shut down the affected engine. The aircraft landed back safely in a single engine configuration, but the situation could have been far worse. The investigation found that as part of the maintenance, the engine borescope plugs were opened during the overnight maintenance activities. But post-maintenance, one of the plugs was not installed back and the other only partly installed. The borescope plugs are removed during, as some of you would know, some maintenance to inspect the internal parts of the engine as part of the engine health monitoring. The fitment of the boro plug is certified not only by the engineer who has fitted it, but also by another engineer who is expected to do an independent inspection and then sign the certificate. Now, here is the critical point. This task required an installation, an independent inspection, and a certification. All three occurred, yet the error still passed through the system. As a consequence, hot gases leaked during flight, causing heavy damage to the engine parts, causing significant disruption and thousands of pounds in repair of the damaged parts. So we must ask, did the risk control fail here? Or did the system fail to detect the failure of the risk control? The subsequent investigation employed the HFACS and the MEDA taxonomies, but could not establish accurately the contributory factors for the human error. The conclusion was distraction of the engineers, and to address that, the MRO issued a high-vis jacket to all engineers that had a statement on the back, "Do not disturb, critical task in progress." This high-vis jacket was meant to be worn whenever an engineer is carrying out a critical task. Now, theoretically, this appeared to be a very good solution. However, there were further similar repeat issues involving independent inspection at the same MRO location and at different locations of the same MRO. From a risk management perspective, this is not a distraction problem. This is a feedback failure problem. The objective of this research was therefore threefold: trying to understand what are the causal factors for aircraft maintenance errors, how do organizational factors influence the effectiveness of the risk controls, and thirdly, in relation to the critical tasks, trying to find out how the risk controls can be made more effective. Importantly, not just identifying errors, but understanding why controls that should work don't always work in reality. To recap, the problem statements are as follows. I gave you one example, but there have been multiple events related to maintenance errors around critical tasks. I've seen key investigations which on one hand would be very limited. We all probably have heard the statement at the end of an investigation, the engineer was reminded about the duties and responsibilities. And on the other hand, the investigations remain inconclusive due to lack of information on what contributed towards a human error. This is due to memory fade. So investigations often are either too simplistic or inconclusive because of memory fade. Now, maintenance errors are in this respect very unique because they often remain latent. They are only discovered later. In relation to critical tasks, we carry out hundreds of independent inspections throughout the year, but have a very limited, if any, feedback on how effective these inspections are in error capture. On the other hand, there is very little useful mechanisms employed in the organizations for identifying weaknesses in skills, and consequently, the continuation training structures in most organizations have very limited usefulness in enhancing the skills. Most of these continuation trainings are focused on enhancing knowledge, but not necessarily the skill behaviors or error patterns. My literature review for the research was focused on topics related to critical tasks in aircraft maintenance, regulatory framework, human factors contributors to maintenance errors, review of key safety investigations, error taxonomies in maintenance, risk controls in maintenance, organizational influence on risk control enhancement, integration of technological tools and a lesson from flight data monitoring implementation, and then also through system perspective theories. So to recap from the example we have discussed, we have risk controls are in place, but we do not have any proactive feedback whether they actually work. The method was multi-layered approach based on qualitative research. The data collection was interview-based with the logic of gathering more rich information. The interview participants were selected keeping in view a good mix. Almost 50% were engineers with varying experiences, and the remaining were a mix of managers and leaders of the company. Now, question arises, why qualitative analysis? And it was considered that because this relates to human factors are quite complex in nature, and in relation to maintenance related issues, it is quite context driven. So they are not always measurable quantitatively. The interview structure was broadly based on three themes. One was the causal factors of maintenance errors. Second one was influence of organizational factors on the risk controls. And thirdly, it was the views on present risk controls, their weaknesses, and recommendations for the future. NVivo software was used to help in carrying out thematic analysis, as it enables to extract the data from different sources like interviews, audio and video files, and helps to construct codes, themes, and presents the output quite visually. In short, therefore, the thematic analysis allowed pattern recognition and hidden relationships. This slide shows the overall thematic analysis output picture from NVivo. Now, it has quite a lot of information on the slide, so you may not be able to read it very carefully, so I'll take you through what actually the result chart shows. I tried to fit this in many ways, but no matter what I did, the words was coming not big enough. So what it shows is types of maintenance errors, and it bucketed into different things like damage during maintenance, variation from approved procedures, tooling related errors, etc. Part of it shows the causal factors for these kind of errors taking place, and they're related to complacency, working through the night shift, ineffective coordination between the teams, poor task instructions, weak training processes, and perception of time pressure. It shows the recommendations and suggestions for improvements, which is things like improved task completion feedback, efficient and better communication, and system design improvements. The result tries to capture the best practices which ensure a higher effectivity of the risk controls, things like better control of critical task accomplishment, smarter tool control processes, and efficient communications. It also shows how leveraging the technology for some of the processes can reduce the risk of maintenance errors, like using digital twins, smarter use of technology, and using pictures and videos, mechanisms for proactive warning of maintenance errors, e-tech log, etc. So in short, errors identified were procedural deviations, tooling errors, damage during maintenance. Causal factors were complacency, night shifts, poor coordination, weak instructions. And something to note is that these are not isolated. So for example, if there is an issue of fatigue combined with poor instruction, that automatically increases the risk of misinterpreting the task content. Some technology insights which came about were opportunities in terms of digital logs, visual confirmation, and predictive alerts. So if we view the maintenance safety through the systems perspective lens, the question becomes not where the failure occurred, but why the system did not detect it. That leads into the key discussion points. Now this slide tries to summarize some of the key results from the research. Complacency figures high on the list at 33%, but other key observations were ineffective training, communications, shift timings during the night, Something to notice that complacency is not negligence, it is a normalization of a routine. So a key message from this slide is risk increases when tasks are repetitive in nature and errors may have no immediate consequence in the maintenance world, as in the topic we are discussing now. This slide shows challenges in risk control implementation. So again, from the results, so post-COVID challenges in retaining competent engineers, it has seen experienced engineers leave the industry. Actually, just before this presentation started, Cengiz and myself, we were discussing how experience have disappeared from the middle complete section of the engineering world. So whereas mitigations like recruitment through the apprenticeship schemes has started to yield good results, however, the time to gain the skill maturity is difficult to expedite. There is no shortcut to getting experience at a very short period of time. Along with the above, there is the issue about resistance to change. This factor affects in terms of adoption of new technology. So if you imagine we have people with greater experience of, let's say, 40 years of experience in doing this work, and then on the other hand we have freshers who are trained, who have gone through the courses, who have gone through the licensing system, and quite a young age profile of the other group. So there are different acceptance factors in relation to new technology. In the previous slide, some causal factors mentioned was complacency, time pressure, and the night shift duty times. Therefore, a key observation in the study was the over-reliance in some cases of another engineer's work that could result in tasks getting certified without completion to its intent. In short, there is an assumed assurance: if it is signed, it must have been done, as was the case in the boroscope plug example. Therefore, the observation was the possibility of a feedback error and the weakness of the error capture method of independent inspection. So the research found similarities with some of the existing studies, like the types and causal factors for the maintenance errors. It also observed that value added by the HFAX model, which has been derived from the Swiss cheese model, in understanding the organizational factor. The model it observed was also successfully applied for investigation in most of the operationally linked safety events. However, my study observed a fundamental weakness in the practical applicability of the model related to maintenance errors. These errors are seldom detected at the point when the error is made. Rather, they come to light as a result of flight safety incident or during a subsequent maintenance check. Due to memory fade, the investigations very seldom are able to establish the actual reasons for unsafe acts. A key limitation identified, therefore, with traditional model applications such as HFAX is the reliance on retrospective identification of unsafe acts, which is particularly challenging in maintenance due to memory fade and delayed error detection. To overcome this, the STAMP model was introduced as a complementary systems-based approach. So STAMPs, again, for those of you not conversant with the term, it's System, Theoretic, Accident, Model, and Processes. It's a systems-based approach, and STAMP views safety as an emergent property of effective control and feedback within a system, and suggests that accidents occur when control actions are inadequate or when the feedback is missing or delayed. So I'm not sure if you can see my cursor. So that's what that's what in effect it says, that if your feedback is good, your control actions are properly managed and controlled. It's the control process. In this context of aircraft maintenance, this perspective is particularly relevant, as certification without meaningful task completion feedback represents a weak or broken feedback loop within the safety control structure. This systems perspective helped frame maintenance error not as an isolated human failure, but as predictable outcomes of inadequate feedback within the maintenance assurance system. So from a systems perspective, safety is maintained through the continuous control and feedback rather than reliance on procedural risk barriers alone. To make the systems perspective from a previous slide more tangible, I've summarized it here as a simple feedback loop model within the maintenance context. On the left, we start with task execution. This is where the maintenance activity is physically carried out. This is supported by controls like procedures, independent inspection, supervision. These controls lead to certification, which is how we currently confirm task completion. This is where the key issue lies. In the current system, there is limited quality feedback between certification and actual task outcome. We effectively assume if it is signed, it is complete. The proposed model strengthens this by introducing enhanced feedback mechanisms such as digital confirmation, visual validation, data-driven or AI-supported insights. These mechanisms allow us to move to control validation. Not just was it signed, but was it done correctly? This validation generates meaningful feedback outputs, which feeds into risk control improvements, targeted skill-based training, organizational learning, and importantly, the loop then feeds back into the future task execution, as you can see on the screen. So safety is no longer a one-time confirmation at certification. It becomes a continuously validated system of control and feedback. And if this feedback loop is weak, errors can remain latent, but if it is strong, we gain real visibility of control effectiveness, which leads directly into the key discussion points. These slides bring together the key discussion points from the research and explains why the current approach to maintenance assurance needs to evolve. The first key point relates to the post-COVID operating environment, which was a strong and consistent theme across most of the interviews. Organizations are facing a shortage of competent and experienced engineers, not just in terms of numbers, but in the depth of experience, as I mentioned before. Many senior engineers have left the industry during COVID, and while recruitment and apprenticeship schemes are now recovering capacity, the skill maturity cannot be accelerated easily. As a result, tasks are increasingly being performed by lesser experienced engineers under higher workload, with greater reliance on procedures and supervision. This makes the effectiveness of task feedback and assurance mechanisms even more critical than before. Secondly, it's the supply chain constraints. Alongside workforce challenges, supply chain constraints were highlighted as an operational pressure. Delays in parts availability increased time pressure, task fragmentation, shift handovers. These factors indirectly increase the risk of incomplete or improperly closed tasks, particularly on critical maintenance activities. A central finding of this research is the inherent weakness in the way task completion is currently assured. Certification today is largely a binary outcome, signed, not signed. What is missing is a quality feedback. How well was the task performed? Were there difficulties, deviations, or uncertainties? Did the independent inspection genuinely verify task intent? A signed certificate tells us the task was declared complete, but it does not always tell us that it was completed correctly. This creates a false sense of assurance, particularly when errors remain latent until a later event. These findings point clearly to the need for a new systems-based approach to maintenance assurance. Rather than adding more barriers or paperwork, the focus should be on, the research felt, enhancing the task completion feedback loop, making control effectiveness visible. Technology and artificial intelligence can support this shift by enabling visual or digital confirmation of critical task completion, real-time validation of task closure, early identification of task-level skill gaps. Importantly, this feedback should not stop at compliance. It should feed directly into targeted skill-based training, risk control refinement, continuous improvement of maintenance processes. In summary, the discussion highlights that the challenge is not the absence of control, but the absence of meaningful feedback on how well these controls perform in practice. This sets the foundation for the conclusions and the recommendations, which I'll cover next. I'll conclude by drawing together the key findings from this research and placing them in context of existing safety models and airworthiness assurance. Models such as HFAC's, MEDA, and Reason's Swiss cheese model have made a significant contribution to aviation safety. They have helped the industry move beyond the individual blame, understand organizational, supervisory, and environmental influences. These models remain very highly valuable, particularly for event investigation, identifying systemic weaknesses, informing safety management systems. This research does not challenge the value of these models. On the contrary, it reinforces their importance. However, this study highlights a practical limitation when these models are applied to aircraft maintenance. Many maintenance errors are not detected at the time of when they occur. They are only discovered later through a subsequent investigation, inspection, or a flight safety event. And by the time an investigation takes place for that, memory fade has already taken place. There is a lack of task level evidence. There is a limited feedback, which makes it difficult to reliably reconstruct the original unsafe act. As a result, even well-established models can struggle to explain why a task was certified as complete, whereas in fact it was incomplete. So the central finding of this research is that task completion assurance is a weak point in the maintenance safety system. Certification and independent inspection provide a declaration of completion, but often there is no confirmation of task quality or task intent. This allows errors to pass through existing control and they remain latent within the system. In other words, the issue is not that we lack safety models or controls, but that we lack feedback confirming that these controls have actually worked. This research supports HFACs and similar frameworks by addressing what happens before an investigation is required, strengthening the system's ability to detect errors earlier. By assuring task completion, oh, come on. Excuse me, my phone rings and it's not. Sorry for that. My phone refused to stop the rings. By assuring task completions, organizations can reduce reliance on retrospective reconstructions, is what I was meaning to say, and they provide more accurate inputs into investigation and learning. So assuring task completion strengthens the foundation upon which models like HFACs operate. From an airworthiness perspective, the findings suggest that compliance alone is not a sufficient indicator of safety. Assurance must include evidence that critical tasks were completed as intended. Improving feedback loops enables us validation of control effectiveness, earlier detection of skill gaps, and more targeted skill-based training. This brings me to the last slide with a final thought. In conclusion, this research suggests that the future of maintenance safety lies not in doing more inspections or adding more procedures, but in knowing with confidence that critical tasks have been completed as intended. Thank you very much. And there is a link which I have in this presentation, which if this gets distributed, you will see the link there. And I can also copy it into my into the chat line. And now I'm open for any questions if you have for me.
Thank you very much, Raj. That was excellent, and I think you very clearly expressed your findings. It looks like you have a question. Well, you have a round of applause there from everybody who's online.
Thank you.
Certainly, there's a question in the chat, I think, there at the moment. So if you'd like to have a look at the chat, you might like to address that question first.
Sure. Okay. First one said this needs. There's a link, John, which you have posted, which I'm not sure what that relates to. This needs updating. It says is that's from yourself.
Oh yeah, that was a paper that was published some time ago by the Aeronautical Society on
Okay.
human factors in this area. But bypass what I put on there, and I think there's a question from Tom Deacon, and well, Tom, you might like to express the question yourself.
Please go ahead, Tom.
Hiya, can you hear me?
Yes, I can. Yeah.
Ah, perfect. So I was just sort of really thinking that as engineers, it's a common psychology thing is system one thinking and system two thinking. What's conscious and what's not conscious. And quite often, when I drive home, I don't think about driving, I just drive. And sometimes it's the same with sort of aircraft maintenance. It shouldn't be that we slip into system one, but it is completely human nature. It's normal behaviour. It's system one thinking. We're not aware of it. So I think when you talked earlier on in the slides of memory fade, I think it might not be that the memories fade. It's just we were never conscious of it in the first place. We don't know the reasons why. We just slipped into autopilot, and we were subconscious of our mistake. So it kind of, I completely agree with the recording of media and the way of kind of using glasses with cameras or what have you built in to sort of detect that you've left a boroscope plug off, because you might not even be aware of it. It's very difficult because it's the process. And sort of fixing it that way, but also the culture and kind of getting in the habit of either leaving a boroscope off or on. I think you're right. I think the recording of the media is essential. So yeah, my question, sorry, I've ranted. Is it conscious? Is it possible that we weren't even conscious that we made the error in the first place?
So it's a very good question actually, Tom. The memory fade aspect which I was referring to there was essentially related to if you have an event which relates to maintenance activity, from the point when the activity has taken place to the point when an event has taken place, some time has already elapsed. And so at that particular point in time, if you're trying to re-establish what was the contributory factors why a human error has taken place, it almost becomes like a second guess. And so quite often you might find, and in my experience I've seen, that investigations either remain which relate to human factors, and they have a conclusion like it. Either they say it's inconclusive because the contributory factors couldn't be properly established, or they could go the other way and say we have sent a message out to all the engineers reminding them that this procedure has to be followed. Now engineers already know that this procedure has to be followed. We don't have to say that. So most of the time the investigation, which in reality should be a mechanism to enhance the organizational learning or enhance the risk controls which are in place, those investigations become, for the want of a better word, almost like a waste of time, because you are unable to establish what was the contributory factor. So the memory fade term which I used was in relation to that, because unlike a flight crew, if they do a mistake, it's immediately visible to them, or something will record it and it's visible. So they are in a much better, much quicker time. They can actually relate, okay, this is what was distracting me and this is what happened, that's why I did this mistake. But in the case of an engineer, because the time has gone past, and most of the time it may well have been after a night shift, and maybe you have we only find out about this problem a week down the line. So even in the boroscope example which I gave to start off with, this event happened the next day when the aircraft flew. So after a night shift, the aircraft flew, and even in such a short period of time, the human brain doesn't kind of log everything, what are the contributory factors. So when the engineers were interviewed, it was inconclusive. So they couldn't really establish. So they went for the next best thing, which they thought, okay, let's put a high vis jacket which says critical tasks do not disturb. But lo and behold, at the same MRO location, the same errors on a different critical task happened again. So it wasn't clearly a very effective risk control. And so this systems theory says that, okay, let's put it this way, everything which we do, some human being is doing some activity there. So from time to time, there will be occasions when a mistake will happen. So what you're trying to, so on one hand, you're doing everything to ensure from an organizational perspective, from a supervisory perspective, from task instructions perspective, you are following methodologies like HFACs to ensure that everything is in place so that the possibility of that human error is reduced. But with the systems theory, which my presentation showed using the STAMP model, what it says is that if the human error has taken place, how do we know it has taken place before a flight event happens? And that is, so it is trying to address it from the other side of things, that okay, if so what it says is that to manage my risk properly, I need to ensure my controls which I'm putting onto my task is always accurately managed, and that relies on the feedback which is coming in to ensure that I'm getting the correct feedback. So I hope it makes sense, Tom. It was a slightly longer answer. Your mic is on mute. Sorry.
No, that does. That makes very good sense. It's very interesting actually, Rod. I'm fascinated by the subject, and thank you very much for your answer.
Thank you, Rudo. Hi, Rudo. How are you? First of all.
Hi, Raj. Good afternoon, everyone. How are you?
How can existing controls in industry be enhanced following these findings from the research, and will take implement to? Okay, so something to note here is that what is being recommended is very scalable in nature. So it is not actually saying that we have to establish a massive system to start doing that. This is very scalable in nature. It can start with something simplistic, things like video capture or a picture capture of the last stage or the critical stage of a critical inspection. So for example, in the boroscope plug, it could be something like capturing the picture of a locked boroscope plug. On a different example, if it is like putting the correct torque value on a particular bolt, there are many torque wrenches which are available now even in the industry, which can automatically send a signal to a computer like maintenance information system to say that it is expecting a torque range from, let's say, 40 to 60 pound-inch, and if it is outside that range, it will kind of give a bleep to say it's a wrong torque selected. So what happens is that will not allow the engineer to certify that task without having to check it again and kind of that signal coming through again. So there are various things. So you for a smaller organization, for example, they can start with something very simple like a digital or visual confirmation step, a recorded check, something which requires like a torque wrench, like giving an outside range signal, or something which probably at the stage one, if it's a small organization, need not be validated for every independent inspection task. But when you come to investigation of something after something has gone not as expected in a flight, then at least you have proper data to establish what was the contributory factors, as opposed to trying to second guess at that time. Does it make sense, Rudo?
Yeah, it certainly answers the question. I think the only other thing I'd like to understand is the challenges you've mentioned around implementation of that risk control, around resistance to change, and possibly the feedback error, and where that also ties into that same element.
Okay, so the biggest barrier is not technology, it is the mindset. So, and there is a natural tendency to assume that if something is signed, it is complete. So why do we need something to kind of record that? So moving away from the assumption towards validation requires both cultural and organizational change. And I think that is perhaps a bigger barrier, because guess what? for 100 years we have been signing off things, and everything is signed off, and that is the process which is followed. So the mindset of changing from that and adopting this approach, that requires a cultural change and mindset change. So more than the technology which is required, which could be very elementary technology to start off with. I have mentioned artificial intelligence, but that is only as the system matures. All it requires is, if you can imagine, an aircraft comes out with 500 or 1,000 tasks signed off from a base maintenance, and there's possibly 50 of these tasks having independent inspection. So what is not being suggested that you go through every 50 tasks to try and find that it has recorded that evidence or not. But an artificial intelligence in a system like AMOS, for example, can easily scan that in under a minute to say that all the expected evidences are there or not, as well as whether they are in the required ranges or what it is expecting. So if it's a locking wire direction, it needs to it can check it. I mean, if you look at your phone even now, if you scan the phone camera onto a particular word or particular sentence, and you say, I'm looking for this item, it will understand that sentence and it will try to give you exactly the same images of that item which you are kind of trying to understand. So that technology is already available. So coming back to your point again, the challenge remains, which needs to be kind of seen or kind of is a change of mindset which is will be required, as opposed to technology which is already available in my view.
Yeah, maybe one more for you, Raj, before I stop bombarding you with questions as to how do you change the mindset of an organization or a team of people who've been doing something a particular way for a long time?
So again, if we remember the change of the mindset which was required once flight data monitoring analysis became mandatory, that change didn't happen overnight. It took a couple of years, 2-3 years. So the most important aspect of this is culturally, everyone needs to feel that it is not trying to do a blame culture, or it's not trying to catch someone out. It is kind of reinforcing their action. So it is kind of it kind of helps the engineer in kind of reinforcing that action. And there needs to be checks and balances to kind of ensure, quite similar to the flight crew side of things, where there were protocols were laid down to say that that information will be used for better learning, for organizational learning, and not to catch people out, not to sack someone. Because guess what? Wherever human beings are working from, no matter how trained they are, from time to time there will be mistakes. So the idea is that if as an organization we can learn quickly enough, then it can stop other people doing the same mistake again. And to be able to learn properly, we need to be able to understand how the mistake happened. And the best way to go about it is, best chance we have is by trying to monitor this feedback loop. And that will give us something to show the weaknesses and skill, if that's the case. And then that can be fed through the continuation training side of things. But in all this discussion, the engineers who are actually at the front end and the project team, if you like, they all have to be, that trust needs to be there, and people will see the value of the thing, as opposed to, and that's the way I think we can over a period of time, this can be kind of implemented in an organization. So again, as I said, it is scalable, so it does not require that with a one big bang the whole organization goes and adopts that. It can be started from a smaller station, like Rudo, we kind of tried to do a sampling of this in one of the easyJet stations, and so it can start small and then grow as it gets adopted.
Thanks, Raj.
Cheers. Anyone else? With any questions?
It looks like Kevin's got his hand up now. So, Kevin Hayes from Airbus, would you like to raise your question?
Yeah, sure. Hi, Raj. Thanks for the presentation. Really interesting and a subject close to my heart, as you know. You really struck a chord with me when you talked about maintenance certification and saying if it's signed, it's done. Yeah. I'm a big fan of that. Systemic issues need systemic solutions. So the current certification process we have, it's really tailored towards, say, showing compliance. The binary, it's done or it's not done. So, what role do you see the regulator playing, if any, in sort of changing this mindset and adopting this sort of new way of working to this more sort of qualitative approach about how well was the maintenance done or not?
So, well, thank you for the question, Kevin. That's a very, very, very valid question in this discussion. And my view is that there are already enough regulations. So the regulation already covers this aspect. What we are trying to address is a gap between the compliance and assurance. So the regulations already encourage compliance. They already encourage continuous improvement. So what we are saying is that because there is inadequate feedback or inadequate assurance of the activity has been completed, or inadequate assurance that the risk control is effective, that's why we have a gap. So I think within the umbrella of the regulation, it's already covered. And this probably, whenever I have discussed this with the regulatory authorities, there has been a very positive feedback from that. Does that answer your question?
Yeah, no, it does answer it. I guess I was more curious is, could they, they've got existing regulation and it does what it does, but can they better support, this feedback somehow, through encouraging use of tools like you've already proposed, basically evolving the regulation into something more flexible and acknowledges the reality of maintenance rather than so binary?
And again, a very good question there, Kevin. So I suppose the answer should be yes, but the problem, I think, is in an MRO kind of an environment, there's a wide range of MROs. And so we have the matured MROs and the big airlines and the related 145s, where probably something like, if it comes through a regulatory guidance or something, it'll be relatively easier to implement that. But there are many smaller MROs where the challenge will be much bigger, and probably they may not be well equipped at this stage, some of them, to adapt that. And another side of challenge would be that how to like, for example, when we look at the flight data monitoring kind of that, because that became a mandatory requirement, but that had loads of data which was available. So here the question is, we have to generate that data depending on the organization's maturity to be able to then satisfy that. So I think that it'll be good to have the regulatory requirement like that, because to me it appears to be single most thing which can improve the risk margins there. But it may be slightly, depending on the maturity of the organizations, that may fall differently, that regulatory diktat. In the future, I can see that coming at some point, because and that's why this topic is close to my heart, and I like to present this so that this is, and as I said, wherever I've discussed this or presented this, everyone sees the benefit of that, and it is the culture change which would kind of help. So we need a few leading organizations to start testing it out. And I'm not sure, Rudo, how we were, and probably not for this presentation, but maybe I need to catch up with yourself to see how well that test or sampling is going on. But over a period of time, if there's an adoption of this by the matured organizations, then that gives a chance for the regulator to then come down and mandate in some way, shape, or form to kind of say this is a requirement.
Super, thank you.
Cheers.
As an ex-regulator, I don't like necessarily to intervene because I'm an ex-regulator, but SMS, I see this is perhaps part of a safety management system, part of learning. The example you gave is an experience to learn from, and the SMS system should learn from experience and introduce whatever means or mechanisms are necessary to address the identified safety issue. So I don't think the regulator needs to. One of the key pillars of SMS is safety promotion. So perhaps rather than mandating the solution, this is something that should be promoted. That's one point of view.
Yeah, John, I quite agree, because I think from a regulatory perspective, this is already covered through the SMS and through the requirements of compliance, and through the SMS requirements, it's already covered. It is again, I'm probably Kevin may have asked that question in relation to the FDM, because I remember when FDM was mandated, that even the mandating of that thing, it still took a good couple of years, a few years before it was fully implemented. So it is, if there is a regulatory kind of a pressure, then probably the cultural change time span can be reduced, is probably where Kevin was coming from. I'm guessing, yeah, Kevin.
Yeah, a little bit. It's, if you want to sort of squeeze this issue, you need to have a top-down and a bottom-up approach, and there's always a balance between that and who leads. And actually, I think probably in this space that you're right, the mindset of doing maintenance and showing compliance, it's so ingrained in what we do that actually I think you need industry and Part 145s to really show that this works and how effective it is. And then I think you'd probably then see an evolution of regulation where they would go, oh, this is what you're talking about, and then might sort of drag them along. But yeah, I totally agreed.
Well, if we go back to the history of FDM, which is part of my history here at UKCA back in the 1990s, we were actually promoting it, and conducting research. And there was a guy called Dave Wright who used to be dedicated to that task, working with British Airways, the Thesis system. So a lot of the fundamental technical work was done really through promotion and research. It wasn't until things had been more generally adopted that there was a possibility of designing standards and then mandating. And of course, there was harmonization difficulties as well, because the US had FOQA and Europe had FDM. So you have to harmonize, you have to ensure that everybody is going in the same direction before you can go down the mandate route as well. So yeah, it takes time, it really does. I can see Tom's got something.
Yeah, I was just going to say that one of the sort of the barriers to change and the resistance from engineers like myself that are on the shop floor is kind of the lack of a two-way process for kind of it stems from sort of continuation training, which you have to do every 2 years. We click through a CBT, but if there was a face-to-face meeting of minds between sort of compliance and the regulator as well, and sort of engineers at the front floor, where we kind of exchange ideas of why these things keep happening again and again, and understand the need for these new technologies to be implemented, it might kind of help kind of lessen the resistance to change. I think the more kind of compliance driven we are with online training, technology is a double-edged sword. It's got massive advantages and we definitely need to implement them. But if we keep kind of going down the sort of the CBT route and sort of just compliance for compliance sake route, we're going to sort of face these issues, and we're not going to sort of fix them, if that makes any sense.
Tom, I think you have absolutely hit it from a cultural aspect. You have hit the nail on the head. It has to be as where everyone understands. So lots of communication, lots of understanding the need for this change is what will help to drive this thing forward. Is my view also. Absolutely, I think so.
Okay, do we have any more burning questions? I mean, maybe there is something that IFA can do here. It's a sort of subject where a sort of one-page flyer that you could promote might be quite a good idea. And so I don't like allocating tasks, but if we could condense the idea into some simple phraseology and push it out there,
sure.
I think you're absolutely right. Improving feedback, the feedback loop is clearly has advantage, particularly for the condition that you mentioned, the latent failure condition. I can see from a safety point of view, it really is justifiable from the latent failure condition. Obviously other things have become evident, and with more built-in tests anyway, things become evident very quickly when things are done wrong. But the latent failure condition is clearly a serious concern. Any other questions? Well, I think it falls to me to thank you, Raj, for I think what was a very actually extremely condensed. It's a difficult subject. It's a large subject. I think you presented it in a superb way because it's, the message, we've all got the message now. And I hope other people watching this video later will get the message. Clearly, there is some work to be done here. And it does require the softly approach. I get that, because change, it's a very conservative industry, and change in this area does take a long time. So thank you very much for presenting the subject matter today in such a superb way. It's a very small audience, but I think it's the quality of the audience that matters. We can take these messages home and try and do something, and as I say, promote the idea generally. So really, thank you very much for making this contribution. And I think it stimulates further discussion and perhaps further technical work. Yeah.
Thank you very much, John. Thanks.
Okay, let's round up.